In this video and the next, I'll be looking at bifurcation theory. In previous videos, we had taken a bit of look at some of this bifurcation stuff, and I think it's important to take a closer look at them. So here we are looking at local bifurcations in dynamical systems. Local bifurcations in dynamical systems. So straight up, what are we looking at? First of all, what is bifurcation, right? A bifurcation occurs when a small change in a parameter causes a qualitative change in system behavior, and you expect this to happen in, uh, complicated systems like that, right? So we study systems of the form x dot equals f of x comma mu, where x is the state variable. I mean, state variable describes uh, whatever you might be considering, maybe population growth, maybe chemical reaction rate, and whatever, you know. Mu is the parameter that kinds of drive the system, and then f is the nonlinear function. Of course, that's to be nonlinear for this kind of thing to happen. Okay, so a local bifurcation happens near an equilibrium point. So in the last video, right, I tried to explain the idea of equilibrium, right? Using a ball on, on a hill. See, if you have a ball right here, even if it is stable, all you need is push it just a little bit. So a little push to the right or to the left. If you push it forward, it comes into this kind of valley, if you like. And so that little push causes it to change position. But while in this other place, right? If you push it up a little bit, it will definitely come back down. If you push it up this way, it's come back also. So, um, so in this case, we may say this is a kind of unstable equilibrium, while this is a stable equilibrium, right? That's because there's a possibility that when apply a little bit of push, it shifts from this place. Whereas when it comes in here, you need more than a little push to get it out of where it is currently. So that's a rough way of explaining the idea of stability. So here we say a local bifurcation happens near an equilibrium point, and that's what I've explained there in a way. Okay, so bifurcation theory now. Um, so bifurcation theory framework. What is the framework for bifurcation theory? First of all, if you have the system x dot equals f of x comma mu, of course, which is the nonlinear system, like we said already. So first thing you want to do is to find the equilibria. So you equate f of x comma mu to 0, and you solve for all the values, maybe x, y, or whatever you have there. Then another thing you want to do is to linearize. We talked about linearization using the Jacobian method. So to linearize, this is the summary of it. But at the end of the day, you're basically just differentiating each parameter in every function presented with respect to the various variables. I mean, each function with respect to the variables, you're taking partial derivatives. That's what that actually translates into at the end of the day. Okay, so then you have stability after you found the equilibrium point, after you've linearized, you now evaluate. So after linearizing, you evaluate the Jacobian matrix at each equilibrium. Then you can then check eigenvalues to see is eigenvalue less than 0. That means the system is stable. If it is greater than 0, that means the system is unstable. If it is critical, that means eigenvalue is 0. That is, you can really not decide what that looks like. And finally, talk about the nonlinear analysis. So when linearization fails, higher order terms must be used, and then you can also use other things like manifold method and all of that. So since we're talking about bifurcation and it's local bifurcation in this case, right? So you've done all the things you should do as far as local bifurcation is concerned. Now we want to consider different types of bifurcation you can have. Okay, so imagine for saddle node bifurcation, the normal form of that is x dot equals mu plus x squared. So the parameter mu plus x squared. So the equilibria can easily be found when you equate this to 0. You have mu plus x squared equals 0. So you get x, transfer mu to the other side. You have x squared equals minus mu. So x itself is plus or minus square root of minus mu, right? So of course you have an equilibrium that is actually complex, right? All complex. So here we say if, okay, well, maybe. Okay, yeah. So if mu is less than zero, right? You get two equilibria. So if mu is less than zero, you get two equilibria. If mu is equal to zero, you get one equilibrium. And if mu is greater than zero, you get none. So that depends on the value of the mu. Okay. Of course, if mu is less than zero here, that means it's negative, so you can get two equilibria. If mu is equal to zero, you get only one equilibrium, which is zero. If mu is greater than zero, you get none because you have a complex system in that case, and you won't be able to proceed with that. So you only so less than a mu less than or equal to zero is what you're guaranteed to have in that case. Now, for stability, if x, if f sub x, if you differentiate this with respect to it, that's the only thing you have for the linearization. So f sub x, partial x, that's differentiate this expression with respect to x. All you have is 2x. And then if x is less than zero, that is x is negative, it means you have a stable system. If x is greater than zero, the system is unstable. So we can see that two equilibria collide and disappear. So two equilibria collide and disappear in this case. So look at how that can be demonstrated here. You have mu plus x squared right here. This is the main thing we are doing. So dx is mu plus x squared. So you are plotting x against the derivative, that x dot, right? You are plotting that to see the saddle node bifurcation like that with parameter with mu, right? You are varying mu values like that. So if you run that now, then we see what that looks like for saddle node bifurcation. So, and this is exactly what this looks like. You have your zero here now. For mu that is negative, mu is -1, that is blue here. So you see it goes sub-zero. Then for mu equals zero, that lies on that line zero, and mu equals one, you have this green line right here. And that's what saddle node bifurcation looks like. On the other hand, you have what you call the transcritical bifurcation. So the normal form is x dot equals mu x minus x squared. This is now different from mu plus x squared like that we had for saddle node. No, we have transcritical bifurcation. So x dot is mu x minus x squared. So the equilibrium, if you equate this to zero, of course you get x into mu x equals zero. So you get x is zero and you get x equals mu. So if you do the linearization like we always would have to do, so that means if you differentiate this with respect to x, so you get mu minus 2x. So in this case now, at x equals 0, you get f sub x, that this evaluates to mu. At x equals mu, which is another possibility. So if x is mu, you have mu minus 2 mu. So f sub x is minus mu. So in this case, you have equilibria here exchange stability. So in this case now, if you want to visualize this, you just come here. So you have x1, it's 0, so you need to create a matrix of zeros, and x2 is simply just mu. So in that case now, we just plot that using this. You may want to modify this as you like. So you have at 0, there's a switching taking place. So so this black line is x equals 0 right here. Okay. Then for along x equals 0, you have instability, right? Then at x equals mu, okay, whatever your mu can vary. For x equals mu, this is one value here. So this is the stable leg of it, but still at some x equals mu above. So imagine if mu is from -2, if mu from negative infinity, I can say from negative infinity to 0, you have an instability like this. But then once mu switches from once x is no longer 0, okay, mu now, once mu is no longer 0, mu is now so a bit above 0, then you have another stable leg of it again. So you have, those possibilities like that. Okay, so that's for transcritical bifurcation. Now we move then to the other one, which is okay. Now we talk about pitchfork bifurcation. For pitchfork bifurcation, we have the normal form, which is supercritical. You have x dot equals mu x minus x cube. So the equilibrium would be solving this. You have x into minus mu minus x squared, which is 0. So x is equal to 0, and then x is plus or minus square root of mu, right? So, and then the stability now, you have f sub x equals mu minus 3x squared. Okay, if you differentiate this now, you have mu minus 3x squared. So here we have the central equilibrium loses stability and two stable branches appear. And then this bifurcation requires symmetry. So in this case now, you have a pitchfork kind of thing appearing. So to visualize that here, you have, you have this plenty thing. So first of all, you have, so we have the equilibrium, one is zero, right? The other is plus or minus mu. So you have x is zero, x of zero is this. Xp, you have square root of the maximum of mu or zero, whatever that is. The next term is minus xp, you know. Um, and all that now you try to plot for different values of mu less than zero, mu greater than zero, mu greater than zero, mu greater than zero. So you pair them up like this: mu less than zero and x naught for mu less than zero and all that. Then, I mean, I'll just do this plot and then I'll allow the plot to speak for itself. So if you're interested in the code, you may want to look at it a bit more closely. So, but then when we run that, these are the kind of things we get. First of all, we have this supercritical pitchfork bifurcation. So you see that for along this line, uh, x equals zero, you have stability. But then when it gets to this point, 0, 0, right? So this blue wing, so uh this shows stability both up and down, whereas you then so in the middle, so it's easy to be stable along zero, x along x equals zero, right? So up to this point, it is zero, it is stable, but beyond this point now it becomes unstable again, like that. So that's the supercritical pitchfork bifurcation. So then we move on to see another part. So we can see some dynamics after pitchfork. So where for mu equals 0.5, for instance. So if you choose mu to be 0.5, at x naught equals minus 1.2. So, you know, this blue line now, it goes and then it just merges here. So this one also goes. So you have those things, you have these dynamics after pitchfork. So after the bifurcation, so at the end of the day, everything still goes settle somewhere. So like that. Then we also have Hopf bifurcation. So for bifurcation now, Hopf bifurcation occurs in two-dimensional systems with the general form x dot equals ax minus by, y dot equals bx plus ay. So a very good example of this would be maybe like a pre-predator situation, I suspect. So you can have eigenvalues lambda like a plus ib. So hop occurs if a of mu, is equal to 0 and b is not equal to 0. Okay? So a of mu is 0 and b is not 0. So the normal form then becomes z dot equals mu plus I dot I omega multiplied by z plus bz z absolute value of z all squared, like that. Okay, and then you can also have it in polar coordinates using z equals r e raised by I theta. R dot becomes mu r plus b r raised by 3, and mu dot is omega. So this is like another system of equation in r and omega. So and this in this case now a periodic orbit is created like that. Okay, so, but then we still go ahead to look at supercritical versus subcritical Hopf. So for supercritical Hopf now, you have, from here we see mu r plus beta r cube, right? So for supercritical Hopf bifurcation, you have r dot to be mu r minus r cube. So it's more like the beta is now minus one, if you like, if you compare it with this. So the stable equilibrium for mu less than zero. So if mu less than zero, you have stable equilibrium. Then stable limit cycle of mu greater for mu greater than zero. So you have a stable equilibrium for mu less than zero and stable limit cycle for mu greater than zero. Okay. Then for subcritical Hopf bifurcation, you have so beta now be so from here beta looks like 1, right? So you have mu r plus r cube. So you always have unstable limit cycle and sudden transition. So type now, yeah, for supercritical limit cycle does appear for supercritical, and stability and it's always stable. But for subcritical, the limit cycle pre-exists, right? And then it's unstable. So we can look at that from here. So mu r minus r cube. This is for supercritical right here now. So you have this for supercritical. If you take that mu, so I can just run this And then we have this now, mu r minus r cube. So we have something like this, okay? So you have that when mu is minus 1, so you have this blue one here. When mu is 0 0.5 or the orange one, you have that. So it doesn't cross 0 until it takes a step. So look at this now. You have mu r minus r cube. That is supercritical. So if I want to make it subcritical, I just change this sign, okay? So it will now be subcritical. So it's now subcritical, subcritical, Hopf bifurcation. So I run this now and see what that looks like. See what this looks like. Or maybe I think I need to show the two even. So I'll just copy this out and then put it here. Uh, put this here. Then I'll take it back to what this one used to be. Okay, so we have supercritical and subcritical now. Control Z. Yeah. So now we have this. So this is supercritical. So it's showing above 0 for radial dynamics. Uh, and then here we have subcritical. Okay, I haven't run this now. So this is now subcritical. So this is emerging from, so it's going above. This one is coming from above and coming under. So subcritical, supercritical. So you can see what the difference looks like in that case. All right, so we go for center manifold reduction. So center manifold reduction. So when eigenvalue is equal to 0, linear theory fails in that case. I think we saw that much in the previous video. So if you have, and the general system, if you have x dot equals ax plus f of x comma y dot equals by plus g of x comma y. So where eigenvalues of a are 0 and eigenvalues of b are negative, so in that case now, the center manifold will be something like y equals h of x. So, and then we can have the reduced system. So the reduced system will be something like ax plus f of x comma h of x, because now we have taken care of y here. So we can then look at this example right here. You have x dot equals y and y dot equals minus y. Of course, the eigenvalues will be from, we have 0 and minus 1 for this whole system like this. So you have 0 and minus 1 because x here is 0 and y here is minus 1. If you look at the linear side of things. So then we can then assume that y is equal to h of x. Okay, we say y is equal to h of x, which is like, say, ax squared. So we are now taking this term into consideration. So we say y equals h of x, which is ax squared. So the invariance condition can then be h prime of x times x dot. So h prime of x times x dot, uh, x dot here, is equal to y, right? And we know y is ax squared. So h prime of x here is 2ax times x dot, that's 2ax times y, so that's like 2axy. And for 2axy, we have minus hx plus x squared. Minus hx is actually minus ax squared plus x squared, like this. So if you solve all that now, you see that a is equal to 1. So with a being equal to 1, then the reduced equation then becomes, so you then reduce the equation, you have x dot equals x squared, because y itself is x dot, right? And y was ax squared. So if you, after solving this to get a, you have 1. So x dot is equal to x squared. So there's a bit of maths going on here. You want to check that out. So you have x dot equals x squared. And this is now a saddle node bifurcation. So though you couldn't get something straight from here because it was saddle, so finally come here and get a saddle node bifurcation with x dot equals x squared, like that. So to visualize that, right, we now look at this x squared on its own, and then I run this now, and then it shows us this kind of center using center manifold reduction, and we get this thing. So so watch out for what exactly is happening right here, because we are then having h prime of x. So h prime of x is like 2ax times x dot. X dot is y, and we know y again. So that's 2ax multiplied by ax squared. So, and that leads to minus hx plus x squared, and we get solve that to get a, and then you can now have this reduced uh, center manifold reduction. So, in summary, we have the following that so for saddle node, the dimension is 1, 0 eigenvalues, feature creation and destruction, then transcritical one-dimensional, eigenvalue 0, stability exchange happens there at 0. Okay, then pitchfork, we have one-dimensional, 0 again for eigenvalues. So and symmetry is breaking because you have things you have at a point you have symmetry breaking out. Then for Hopf, we have eigenvalues to be plus or minus I omega, then there you have oscillations. And for center manifold, you have any dimension at all for center manifold, right? The eigenvalues are 0, and then the feature leads to reduction. So the standard workflow for this whole thing can now be something like this. You find the equilibria, you compute the Jacobian, you find eigenvalues for each equilibrium point evaluated by in the Jacobian. Then you identify critical values, reduce to normal form, classify bifurcation, and simulate numerically. So in this case, now imagine we have mu x minus x cube, all right, and then we do the Jacobian and do all of these things. So this is how this goes. Okay, we have okay, this shows now. So the equilibria for this particular system, mu x minus x cube, the equilibria are 0 minus square root of mu plus square root of mu. We did this before. And for the Jacobian, we have mu x minus x cube. So with respect to x, we just have mu minus 2x minus 3x squared. And then at x equals 0, so at x equals 0, like that, so the Jacobian at if x is equal to 0, right, being which is the equilibrium, one of the equilibrium, right, at x equals 0. So that's put 0 here. When you put 0 there, you get mu on its own. So you can also do, I guess you can do more printing because here now, if you have this, you have x into mu minus x squared. So you get x to be 0. That's one of the results. Okay, yeah. We can even do more, right? Um so you have df dot subs x comma 0. So okay, I want to try out something. So the first result is 0, as you can see here. So what if we can also do this? What if we do x comma 1 now? In this case now, x is minus square root of mu. Okay, so let me just run it and see what it looks like so I can just update. So in that case, we have mu minus 3. So what if it's x comma 2? That's the second result now. That's 2 here. That's the third result. Mu minus 12. Is that how it works? Like, good. I think that makes sense because now, so this is now x equals minus square root. Okay, we can even do this. Minus square root of mu. So this is mu. So I can make this to be dollar sign here, dollar here, dollar here. Then this is x, dollar here, and dollar here. So now this becomes this is the second result, which is 1 in Python. In Python, can't start from 0. So then this is plus, right? So if I run this, oh, okay. Okay, I don't need all this. So I can just leave it the way it is, right? Okay, I can just say minus square root of mu. Okay, I was hoping this will render some of forgot this is not plot. Okay, so this is minus square root of mu for x there. So this other x now, we have this. And that makes sense, right? Because so if you put or minus square root of mu, so if you square it, that's x, right? If you square it, so you get minus 3. Okay, this is plus now. So this is plus because the first value is 0. So if you put 0 here, you get mu. If you put minus square root of mu, so if x is minus square root of mu, if you square that, that would just be mu minus 3 mu. Is that making any sense? Okay, I guess let me just leave this out and just keep going, okay? Let's keep it moving. Right. Because the equilibrium point will determine what happens in all those places. So at x equals 0, we have mu in short. So final takeaways for that now, we have this. Local bifurcations occur when eigenvalues cross 0 or the imaginary axis. So when eigenvalues cross 0 or the imaginary axis, we have local bifurcation happening. Then normal forms classify generic cases. And of course, center manifolds reduce dimensionality. Then Hopf bifurcations create oscillations, and one-dimensional bifurcations involve real eigenvalues. So we have practice problems. Solve the following problems systematically for each system. Find equilibria, compute the Jacobian, analyze eigenvalues, determine stability, identify bifurcation types, sketch or simulate when appropriate. So let me show them in twos, like you as usual. So here, consider the system x dot equals b plus x squared plus 2x. Find all equilibria, equate to 0 and solve for the x's and do all that. So you have 1 and 2 like this. So this one is another one. So this is for saddle node bifurcation detection. This is transcritical bifurcation. For 3 and 4, you have pitchfork classification going by this. And here you have linearization failure right here. Okay, because you're going to have x squared into 1 plus mu x like that. So linearization may fail because you're going to have x equals 0 there. Then for 5 and 6, you have this. For 5 and 6, you have this like this now. Then Hopf bifurcation and Hopf normal form. Then 7 and 8, you have this. For 9 and 10, this. So try your hands on these things and see how well you can handle them. Okay, try your hands here. So, and you can have possible extensions like this. For selected problems, you can plot phase portraits, compute bifurcation diagrams, verify results numerically in Python using NumPy, Matplotlib, SciPy for simulations. You can follow some of the codes I've shown already even. So with this, I come to the end of this interesting video about local bifurcations in dynamical systems. In the next video, I'll be looking at global bifurcations in dynamical systems. So let's watch out for that. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. If you haven't subscribed, question is why? Go ahead, subscribe right now, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges like having some videos made for just you as a member, being a special person, or you can also be the first to see some videos before other people see them, and so many other benefits like that. So just check them out. There are 3 levels right now that you want to check. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.